Thank you very much, Andres. It's such a pleasure to be here. I can't believe this immense creation, being the vision and hard work and intelligence and diligence of one man, Andres Romer, and the team that supports him so well and does a fantastic job. I was here 2 years ago at the first conference, and I can't believe how much it has grown and become just the world venue for ideas. So I'm very happy to be here and very honored to be here. And I'm especially honored to be here with Professor Jerome Friedman, who, as Andres mentioned, is a Nobel Prize winner in 1990 for the discovery of quarks. Now, I'm a science writer, and every time I write a book, I try to learn the material as much as I can, because I can't write about something without knowing it extremely well. You'd be surprised by, you'd think it's obvious, but many science writers I've met don't believe that you have to master the material to the level that the scientists themselves have. So I've spent many months talking to Professor Friedman and other Nobel Prize winners and other physicists, from physicists working just on small parts of the largest accelerator in the world called the Large Hadron Collider, and up to other physicists doing the theory and the experimentation. So I wanted to say something about Professor Friedman. He was born in Chicago, and he was destined to be an artist. He got a scholarship to the Art Institute of Chicago to study art, and because his family didn't have much money, he needed this scholarship to be educated. But he then read a book that changed his life and changed our life, and that's Einstein's theory of relativity. So he is a young student reading Einstein's book and decided, no, I will be a physicist. And as they say, the rest is history. So I want to explain to you just in very simple terms what Professor Friedman did. And that is he discovered quarks. Quarks are what's in my hand. 3 balls like that, 2 white and 1 black, because there are 2 kinds, and they live in protons and neutrons that make up all matter. So these are particles that live inside something like this balloon. So they live inside, and what Professor Friedman did is to pop the balloon and see these quarks that nobody has ever done before. Now, and Dr. Romer asked me to have a debate with Professor Friedman, but I think the best I can do without making too much of a fool of myself is to try and ask questions. So I'll let him speak.
Thank you very much, Amir, for your very kind introduction. It's indeed a great pleasure to be here today to talk about science and talk about the universe. The universe is an extremely big topic, and I really want to cover it in roughly 20 minutes. And so it's going to be a very fast journey, and the details are not important. What I really want you to take away from this discussion is the concept of what the universe is and the ideas that basically we now have about its structure. So I really want to talk about the structure of the universe, the largest structure and the smallest structure. And so we'll be talking about outer space and inner space. So let me start talking about outer space. So let's go to the first slide here. Oops, I'm sorry. So the question is, how do we find out about the universe? Well, we get cosmological models based upon experiment and observation. And to do that, we have to have observation. So we can look at cosmic rays. These are the particles which come down upon us from outer space. We can send telescopes up into space, like the Hubble telescope, which you see up there. I guess you can see it there. We can send special instruments and satellites also. We can look at it with radio telescopes. And we can have ordinary optical telescopes on mountains. For example, the one in the far right there is the Magellan Observatory on mountains in Chile. And so this is how we try to understand the large structure of the universe. And what have we learned? Well, we've learned that we live on the 3rd planet of a medium-sized star. The star exists in a galaxy which we call the Milky Way. The Milky Way has about 100 billion stars. And the thing which is really remarkable, which we really took a long time to understand, is that this galaxy is only one of many, many, many galaxies. There are 100 billion galaxies, each of which have 100 billion stars. So when you look at the total amount of number of stars in the universe, we call it 10 to the minus 22. So it's actually 10,000 billion stars in the universe. But even at that, the total mass of these stars account for less than 1% of the mass of the universe. So the point is that the Earth, the planet we live on, is less than a speck of dust in the entire universe. And I must say, sometimes when things are going badly, that gives me some consolation. So let me go on here. Here's a picture from the Hubble telescope of galaxies. Each one of these bits of light is a galaxy of roughly 100 billion stars. I mean, and you can just see just how many there are all through space. And now let's go to the next slide. And you see a special galaxy. It's galaxy NGC 3370. There are so many that you give them all kinds of strange numerical names. And this is called a spiral galaxy. And that galaxy has about 100 billion stars. So you really see what the immensity of the universe is. Now, here's, for example, a picture of the Earth. You see this little dot up there compared to the size of the sun. Now, of course, the Earth is much, much further away, but you get a sense of how tiny the Earth is compared to our sun. And our sun is just a medium-sized star. And the other thing which we've learned is that the universe is expanding. It keeps on expanding. And this is because space is expanding. Space is expanding. And the edge is something like 44 billion light years away. But if you looked at it in miles, it's 300,000 billion miles, or 500,000 billion kilometers. That's the edge of the universe from us. It's the edge of the so-called observable universe. And the thing which is interesting is that if we look at galaxies, the further a galaxy is away from us, the faster it's receding away from us. And that's another interesting aspect of it. It's like a bread being baked with raisins, and as the bread expands in the oven, the raisins get further and further apart. Now, what have we learned about the history of the universe? Well, we think the universe started roughly, actually 13.7 billion years ago. It started as a very, very big explosion in a very, very small region, a region that is probably smaller than an atom. And it was immensely hot, and it started expanding very rapidly. And the various particles were produced in the energy, in the great energies of this explosion. And after about a millionth of a second, protons and neutrons formed. And after about 3 minutes, supposedly, according to this model, nuclei formed. It took about 380,000 years for atoms to form. And the reason for this is because the universe, as it was expanding, was cooling down very rapidly. And you see, when things are moving very fast, it's hard for these things to form because they bounce against one another. But when the universe starts cooling down, you can start forming these little things like the atom, like the nucleus in the atom. It's like freezing water. And then 400 million years, the stars started forming, and roughly 1 billion years after the Big Bang, this is the Big Bang model, we have galaxies forming, and now we exist 13.7 billion years after the Big Bang. And the temperature of the universe now, it was extremely hot when it began. It's only 2.7 degrees absolute, 2.7 degrees away from absolute zero. So the universe is actually very big and very cold. Of course, Where there are stars, you get lots of heat, and the stars are producing heat, but the average temperature of space between the stars is 2.7 degrees above absolute zero. So let's keep on going. And the other thing which is interesting, which we have found out, is that not only has the universe expanding, but this expansion is accelerating. And that was a great discovery. It was one of the great discoveries in the latter part of the 20th century. And if you look at this curve in front of us, the red curve represents what we think is the proper behavior of the universe. And it shows us that roughly 20 billion years from now, the universe will be 4 times bigger. Well, it's just a number. But it will also be very, very close to absolute zero, much closer to absolute zero. It'll get much, much colder than it really is now.
Can I ask you a question? The 3 models are: one, the universe will collapse on itself, and that gives us hope for a rebirth, another Big Bang, another. But I understand that because of the accelerating expansion of the universe, that can't happen.
Well, the thing is, there was never enough mass in the universe to have the so-called Big Bang, the Big Crunch. The idea was that the universe has this explosion, it expands out this way, and at some point, it comes back like a spring that's been released, and comes back to a point. And if the universe had enough matter, that would happen. But there's also an additional thing, which I'll talk about in a second, which is causing the acceleration of the expansion, and it prevents it from ever really coming back together. And it's a very mysterious thing.
So we are a one-time experience.
That's right. And so let me go to the next slide, and I'll show you what that is. Here is the energy and matter of the universe. Now, what I want to tell you, you probably all have heard of E equals mc squared. How many of you have heard of that equation? Well, it's the most famous equation of the 20th century, and what it shows is the equivalence of mass and energy. So I can take the universe, and I can say, well, how much energy is associated with the mass? How much energy is there associated with just pure energy? And the thing which is remarkable in terms of recent measurements is that 73% of the universe, 73% of the energy of the universe consists of some kind of mysterious energy which you do not understand. We call it dark energy. 73%. 23% of the universe consists of something we call dark matter, which we don't understand. This dark matter does not consist of atoms. And it's probably some exotic particle which we have not observed yet in the laboratory. So the students in the audience have lots of work to do to try to understand these things. Only 4% of the universe is what we can understand. Only 4% of the universe consists of matter that consists of electrons. And we have a good understanding of that, and that's what we learned in the 20th century. And I'll say a little bit about that now. So the point is, if we say that, most of the universe is not understood. And that's a very significant point. Okay, so what do we know about these contents? Well, dark energy we don't know anything about. We don't know anything about dark matter. Atomic matter we understand very well because the research in the 20th century has uncovered its structure, and I'll talk a little bit about that. And we also know about its constituents. So how have we done it? We've done it with accelerators, with particle detectors, which I don't have time, and so-called scattering experiments. The idea is to have the accelerators accelerate particles to have enormous energies and bang these particles against other particles and try to understand the structure of the particles, try to understand and also produce particles that only existed at the very beginning of the universe, when the universe was very, very hot. So that's what we try to do in the laboratory. And as a result of that, we find out that the accelerators behave like very, very powerful microscopes. The accelerators are like very, very powerful microscopes. I want you to understand that. And that the higher the energy, the higher the magnification of the microscope. The higher the energy, the higher the magnification, and the more we can see, the better the resolution. And that's why physicists want to build bigger and bigger accelerators. It's not because they want more toys to play with. It's because you can probe into space better and better with higher and higher energy. And also you can produce new particles that were only, I shouldn't say new because they existed at the beginning of the universe, but have never been seen in recent times. And so from these experiments, we have developed the so-called hierarchy of matter. We start out with bulk matter here, this chair, everything around us. We consist of molecules and atoms. If we increase the magnification by 100 million, we see the atom. We have to have that magnification. And the atom is something which has a very tiny nucleus with electrons circulating around it. If we increase the magnification by another 100,000, we see the nucleus, and we start seeing what the nucleus is made of. And then if we increase the magnification further, we can see that the particles which make up the nucleus are composed of other particles called quarks, and this is another factor of 1,000 in magnification. So you can see all the magnification that we need to see these things. And the first experiment, with this, one of the most significant, was done by Rutherford in 1911, where he discovered the nucleus of the atom. It was a groundbreaking experiment.
Was this at McGill? At McGill University, or that came afterwards?
It was, I think, in Cavendish.
Oh, in Cavendish.
And the thing is, what he did was he just used alpha particles coming from a radioactive source. He scattered them on gold foil, and by observing the scattering patterns, he could deduce that the atom had a very, very tiny core, and the so-called solar system model of the atom was confirmed. The nucleus was discovered. And next year, 2011, will be called the year of the atom because Rutherford did this experiment 100 years before. And then the proton was discovered in 1919. The proton was found out to be the nucleus of the hydrogen atom. And Rutherford actually was the one who made that observation. And Chadwick discovered the neutron, which is also part of the nucleus, which is uncharged. And that was discovered in 1932. But then the question is, are these fundamental particles? For many years, they were thought to be the fundamental building blocks of matter. But then there were some reasons to think that they were not. And I don't have time to go into those, but to tell you that in 1964, two physicists named Gell-Mann and Zweig independently proposed that neutrons and protons and some other particles were composed of smaller particles called quarks. And the funny thing about them, there were three types. They were up, down, and strange. You know, these are the names they gave to these three quarks: up, down, and strange. Very imaginative, you can see. And the thing is, they had the thing which was really remarkable about them is they had fractional charge. The up was plus 2/3, and the down was minus 1/3, and the strange was minus 1/3. And you see, if you want to make a proton, you would have two up quarks and a down quark. You want to make a neutron, you would have two down quarks and up quark. You can see the charges will add up to be 1 here and 0 there. And that was it. That was the simple model. But everybody said, this is crazy. Particles don't have fractional charge. We've never seen a particle in nature having a fractional charge. So, but of course, these were interesting hypotheses, and physicists always try to pursue interesting hypotheses. And they started searching. They asked the question, are quarks real? So what do you do if you want to find out if a particle is real? You search for it. You look for it. You try to produce it at the accelerators. You look for it in the cosmic rays. You look for it in seawater, meteorites, air, etc. Not a quark was found. Nowhere. And everybody said, that's to be expected. No particles have fractional charges. And so the general point of view in 1966 was that quarks were most likely just mathematical representations, useful but not real. And the point was that particles for neutron and proton were sort of particles which were kind of diffuse particles, and they didn't have any kind of internal structure. So the question is, if you want to look inside a particle to find out what its contents are, what do you do? Let me give you an analogy. If I gave you a fish bowl in a dark room and had water in it, and I said to you, hey, tell me, are there any fish in this fish bowl? You're not allowed to put your hand in, though. You say, what can I do? How do I do this? Then I go and I hand you a flashlight. Well, obviously what you do, you turn on the flashlight and look. And that's exactly what that experiment consists of. Instead of having a light beam, you have an electron beam. Instead of having eyes, you have electronic detectors. Instead of having a fish bowl, you have the proton. And of course, you get the images of the fish. It's reconstructed in your brain. And in the proton, you reconstruct the images of the quarks by using computers.
Do you have to break the proton to see them?
You have to break the proton because what you have to do, this is a technical reason I don't have time to really get into, but you have to break the proton to see it. For many years it was thought that you didn't have to. If you want to ask a question after the presentation, I'll be happy to explain it. But I don't have time right now if I want to finish my talk. And Andres is right down here. He's going to cut me off in a very short time. So that's what you do. And so the discovery of quarks was done by an MIT Stanford Linear Accelerator group between 1968 and 72. And the idea, they used a very, very powerful electron microscope. You know, you use electron microscopes to look for viruses. You can use electron microscopes to look for quarks. And so they examined the insides of the proton and neutron. There was the linear accelerator. The accelerator provided 20 billion electron-volt electrons. The point is the effective magnification was 60 billion times bigger than you could get with an optical microscope. And so that was really why you could actually see something. And so here's the accelerator. It was 2 miles long.
That's where you did your work.
That's where I did my work, and I can't say too much, but it was a very impressive accelerator in those days, and it was so long it had to go over a road. And here are the instruments that were used. This is, in a certain sense, these were the detectors and the spectrometers used. I don't have time to describe them. They were the biggest things in physics at that time, the biggest instruments. They're now dwarfed by other things, and I'll talk a little bit about that. And the whole idea there is very simple. This got a little garbled, but the idea is, if you scatter electrons from see another way of looking at it, if you scatter electrons from an amorphous object. Am I over? Oh, I'm over? Okay. Okay, 1 minute. Okay. So let me just, so the point is, large angle scattering will give you, you can see small objects inside. And actually large angle scattering was found, and therefore quarks were discovered. I don't have time to really go through that. The point is, I just want to make 2 points which I think will be interesting to the audience if you give me the privilege of a couple of extra minutes, Andres. And that has to do with the new way of looking at matter. We know what the size of a quark and an electron are. There's something called 10 to the minus 17 centimeters. To give you an idea, if you expand a carbon atom, which is a very tiny thing, much smaller than a virus, the size of the Earth, a carbon atom, the quark and the electron would both be smaller than 1/4 of an inch in comparison. And so, if you ask the question, you know how many quarks and how many electrons are in the carbon atom. How much volume is taken up by the quarks and the electrons? Essentially, almost zero volume. The little nuggets of matter inside the atom take up no space. So I'm sorry to tell you, folks, you are all empty space. And the thing that I want to tell you about is the following. But you say, well, why can't I put my hand through this particular thing, chair? Because the fields from the electrons in the chair are repelling the electrons in my hand and vice versa. So basically the sense of solidity comes from the fields, not from the little nuggets. This is something, it's a new concept of matter, and that so that we have basically the idea that fields are really what gives us the sense of solidity. Now you'd say, what is a field? Well, you experience the field by having a magnetic field and a nail, a magnet and nail. You can feel the field is a source of force. So that magnetic field is pulling the nail toward the magnet. The same field is holding electrons in orbit, and that's what gives you the sense of solidity. One more thing, and then I will call it quits, because, and we'll have to. What about weight? We know the mass of all the electrons and all the quarks in you, and therefore we can say if you take a 150-pound person and you weigh the quarks and the electrons in that person, what do they weigh? They weigh 3 pounds. So where does all the other weight come from? Where does your weight come from? Well, it doesn't come from the quarks and it doesn't come from the electrons. It comes from E equals mc squared, because the quarks are moving very, very rapidly. And the energy of the motion has mass, gravitational mass. It gives weight. The force fields which hold the quarks together also has energy, has weight. And therefore, it comes from E equals mc squared. One other question, do quarks have anything else inside of them? And then I'll be finished, Andres, and you'll be happy.
Thank you very much.
But let me just make one statement.
Please. That time doesn't matter. No, I'm just kidding.
Time does matter. But the point that I want to make is that we have a certain reality. But the universe that underlies this reality is incredibly strange and mysterious. And it's something that is so awesome that I think it should attract all kinds of people to continue studying it. Thank you.